Action. So this is biases and Fourier coefficients of elliptic curve L functions. I can check with my former students to see if the bet is still active. It's on the order of $10 or $20 as to is this conjecture true or false. What you have to be very careful about is small cases being misleading. So here's one of my favorite examples. My Williams students have heard this before. In lowest terms, what's 16 over 64? 1/4. This should be a little bit faster, guys. Come on. This is, small R U. This is not Hoboken or Dinkum or Western Matter U or Grand Lakes University. 19 over 95. It's 1/5. Come on, guys. Come on. 49 over 98. Okay. 12 over 24. 1/4. All right. 16 over 64. Cancel the 6's. That's 1/4. 19 over 95. Cancel the 9's. 49 over 98, cancel the 9's, and then simplify 1/2. So 12 over 24, cancel the 2's, and it's 1/4. No, not even close. Just because something holds for a while does not mean it will always hold. If you're ever trying to fool somebody like this, what you can often do is you give 2 examples and then you keep a 3rd example in reserve. How many of you have heard of the Euler prime-producing polynomial, where like the first 41 values of this polynomial at integers are prime? If you want, and then something like that, and then the next one is composite. So if you're trying to convince people that it always generates primes, don't stop at the last one that works. Stop like 3 or 4 beforehand. So well, okay, here, if you're skeptical, let's go a little bit further. All right. So there is danger about being misled from small values. So the conjecture I'm about to tell you, it could be complete bullshit. And it might just be looking to be true because I'm looking at very special families. These are families where I can do constructions. So this is related to some stuff I was doing in my thesis and then continued with some colleagues some years later. One of the big things in elliptic curve theory is to try to construct families of elliptic curves with high rank, with high vanishing at the central point. And I found a new way to do this. And this was using some explicit constructions where you could calculate certain sums exactly. So the families I'm looking at are highly non-generic families of elliptic curves. They're families where I can do these calculations. Normally you can't do these sums. So maybe that's why things are being misleading. All right, so the bias conjecture. So one primitive family of elliptic curves, it's something of the form x cubed plus a of t x plus b of t is y squared. A and b are polynomials with integer coefficients. Every time I choose a value for big T that's an integer, I get a specific elliptic curve, or at least I do so long as a certain associated quantity is nice. Every now and then you're going to have a degenerate elliptic curve. We're not going to really worry about that. Everybody has slightly different normalizations. The rth moment of the Fourier coefficients, for each one of these, I'm going to count how many solutions essentially do I have mod p. I'm going to raise it to the rth power. Right now, the actual quantity I'm looking at here doesn't really matter. If this is a project you're interested in, you will, of course, carefully look at things. If you want to talk about the rth moment, you might want to divide by a 1 over p, because we're summing over t mod p. There are p possibilities. You might want to just put in that weighting factor. It's not a big deal whether or not you have it or you don't. It just affects how you normalize things. The other thing is we talked about for L functions, do we normalize the L function to be from s to 2 minus s or s to 1 minus s? These APs are of size root p. They're in fact at most 2 root p in absolute value. You often would divide each of these by a 2 root p, so you would have something between minus 1 and 1. Again, not a big deal, but you want to be aware of the normalization. So there's some big conjectures that basically say if things we expect to hold, then you can interpret a lot of these quantities in terms of giving the rank of the elliptic curve, giving how often it vanishes at the central point. So I'm not going to really go into that right now. I'm just going to say that these things exist. The first thing we want to look at is essentially these first moment sums. So A1 is going to be just taking these to the first power. And so we multiply by log p, we divide by p, we sum over all primes at most x, we divide by x, and that should converge to the negative of the rank of the elliptic surface. So what this tells you is these numbers are actually going to have a negative bias, a very small negative bias. If they are 0, then you'll have a rank of 0. Then the question becomes, how should we calculate these? Well, remember how I said we weren't dividing by p? Here's the division by p now. So imagine all of these numbers when you divide by p. Imagine the first moment was always negative 5. Then you'd be summing log p up to x times negative 5. All right, you pull out the -5, and you'd be summing log p up to x. Well, we just talked earlier today about, when you sum primes, you want to have a log weight. And the sum of log p up to x is about x. The sum of 1 over primes up to x is about x over log x. This difference of logs is coming from this log p weight. So this is the first moment. And so what this is essentially telling us is, if I can take a family where I can calculate A1E exactly, I can use that in certain circumstances to actually get the rank. Normally the way people get ranks of elliptic curves is they actually construct independent points, use something called the determinant of the height matrix. You show it's non-zero. This allows us to bypass all of this. It's a nice construction. Typically in these families you get that this is equal to negative RP plus a small correction term. The p is canceled, the negative r comes out, and there's the rank. Okay. You can also look at the second moment, and Michel showed that as long as this associated quantity to the elliptic curve j of t is non-constant, you get p squared plus a correction of size p to the 3/2. And I unfortunately showed that there are some families where the correction is as large as p to the 3/2. Okay. It turns out there's a cohomological interpretation for what's going on. There's a term of size p to the 3/2, p, square root of p, and 1, but it's not necessarily the case that all these terms are non-zero. In every family I've studied, the first term that doesn't average to 0 has a negative average. So here's a couple of examples. So here's some definitions about what various quantities are. Here's various families. The first is a 2-parameter family. Then you've got a bunch of 1-parameter families. These two ones over here have j of t as 0, so Michel's theorem doesn't quite hold. You don't get p squared, you get twice p squared half the time and 0 the other half of the time. So this is a very nice generalization of Michel's theorem that holds. And then the values for A1E, these are all families that I have very carefully chosen to be able to do the calculations. It's 0, then negative p, negative 2p. There might be one later on with a negative 3p. All the stuff over here, you can see lots and lots of negative signs. Now this one over here, this does have a positive sign. It's plus c 3/2 p. So we're going to look at what is c 3/2 p. So if you look at that, it's p times this quantity over here. This quantity here is the Fourier coefficient of an elliptic curve with complex multiplication. It averages to 0. It will be of size square root of p. This term will be of size 3/2. This is why I gave the term the name c sub 3/2 to just indicate that's the power of the prime that occurs. So this does have a term that is not 0, but it averages to 0. Here's a more interesting one. It depends on what the prime is congruent to modulo 6. But it does have a negative average. So we then try to look at why you might care about this. Why was I looking at this in my thesis? Well, this goes back to the one-level density we were talking about a moment ago when you were looking at these convergence. We said random matrix theory gives you the main term. Well, these low-order corrections, this gives you some understanding of how you converge to these random matrix theory values. And it turns out that these corrections will give us a small understanding of why we seem to observe more vanishing than expected at the central point. In the limit, it's going to vanish, but for small values, it's going to be there from this bias. But it's such a small amount, it's not really explaining the incredible extra vanishing. You need other theories. This is the finite conductor theory I was alluding to last time. All right, so implications for excess rank. I'm not going to go into this too much. Methods for obtaining the explicit formula. So if I have an elliptic curve, these numbers are defined as follows. It's negative the sum of x mod p of the following. So this is the Legendre symbol. It's 1 if this is a square mod p that's not 0. It's 0 if it is 0 mod p. And it's negative 1 if it's not a square. So if you think about it, how often do you expect this number to be a square? Half the time. And we're not going to worry about 0 because that's half the time it's a square and you get a contribution of 1. Half the time it's not a square and you get a contribution of -1. So if you were to look at 1 plus this symbol, 1 plus the symbol, if it's a perfect square, you get 2. If it's not a square, you get 0. Well, if it's a perfect square, I'm trying to solve this expression mod p. If this is a non-zero square, how many choices of y do I have? So if it's a non-zero perfect square, how many choices of y do I have that will square to that? 2. The square root and the negative square root. If it's not a perfect square, then no values of y work. So 1 plus this symbol is going to be related to how many solutions there are mod p. So this quantity is really counting how many solutions there are mod p, and it's taking into account the fact that we expect half the time there to be a solution, and when there's a solution we expect there actually to be 2 solutions, and half the time we expect there to be none. So you would expect the number of solutions to be of size p. The fluctuation should be then of fluctuating around that, maybe of size square root of p, and that turns out to be the case. And so it turns out if the sum is linear, it's very easy to calculate. Whoops. If I have something in the form ax plus b, if a is not 0, it just averages to 0. If I have ax squared plus bx plus c, again, we can do it for a quadratic sum. It's not that hard to do this. About half a page of calculation. Once you have a cubic or higher here, we no longer have closed form expressions for these in general, and this is why elliptic curve theory is so painfully difficult. But we have explicit formulas in these cases, and I can use this by constructing families with the polynomials a of t and b of t very nice in terms of t. I can actually do these calculations in closed form. Okay, and so for a lot of different families, we can actually calculate what we get. So here's calculating what the second moment would be for one of these families, and you can see this really nice quantity. You can see the negative sign over here. And then, just lots of different families. I'm not going to go through too much detail here. If you're interested, you look at the paper, you look at the slides carefully. In a lot of these families, we're able to calculate things. We're able to see what's going on. And we keep seeing this negative bias. We keep seeing all these terms averaging away. You can look at other families. You can look at families of Dirichlet characters. You can look at families of cuspidal new forms. And you see different biases as well. You can look at symmetric powers. So a lot of these calculations are not going to be that bad. And the question is, can we find the correct normalization? So I think we used the wrong normalization in the past, which means the papers have to be rewritten. This is similar to the stuff we had in number theory and random matrix theory. What's the right quantity to look at? We want to look at the sum over distinct indices. That turns out to have the nice connection. For the biases, we want to look at what is the right quantity to view. Okay. So that's really all I want to say on biases. Any questions? Okay, can you hit stop?